Welcome back to STEG's virtual course on key concepts in macro development. STEG stands for Structural Transformation and Economic Growth. It's a CEPR-led research program funded as part of the UK aid effort by the Foreign Commonwealth and Development Office of the United Kingdom. We're thankful for financial support from them. We are also thankful to have Lauren Berquist and Eleanor Wiseman here today with us. If you've been following the course, last week, David Lagakos talked about the agricultural productivity gap, and Chris Tonetti gave us an overview of macro models of technology diffusion. Lauren's going to push toward micro empirics. What do we know about technology adoption in agriculture in particular? Eleanor is the TA for the class, and she will be giving a session next Wednesday, and she'll also be answering questions in the Q&A. As usual, if you're joining in the front row as a panelist, please mute your microphone, but feel free to unmute if you have a question or a clarifying question especially. And Lauren will leave some time, 15 minutes at the end, for questions. Those of you who are joining through the webinar, you can enter questions into the Q&A. Eleanor will be helping to answer those. Doug and I may also take a crack. And if there's questions that we find, either more difficult or they're broader questions that we'd like to bring them up to Lauren, we'll do so at the end. I want to thank Mandy Chan from CEPR, also Kirsty McNeil and Lauren Waring for helping organize the course as always. And especially thank you to Lauren, who's really doing this again. Everyone who's teaching this is teaching it out of the goodness of their heart. With that, Lauren, why don't you get started and share screen?
Great. So can you all see my screen? Great, perfect. Yeah, so thanks so much to Joe and Doug and Mandy for organizing this great course, and thanks very much for inviting me to participate in this. It's really an outstanding course, and I think the level of interest by the number of students has been pretty amazing. So great to see you all here. So yeah, so today I'll be talking about barriers to technology adoption, specifically in agriculture, and what we know from micro empirics. So before we dive in, let me give you a big picture on what we'll be talking about for this lecture. You may be wondering, why are we talking about micro evidence in a class on macro topics? So I'd like to sort of motivate this in two ways. The first is that agricultural technology adoption is an area in which, especially over the past couple of decades, we've really generated a very large amount of well-identified evidence coming from natural experiments, coming from RCTs, on the constraints or barriers to technology adoption. So it's really a place we've got a lot of micro evidence. I think this is potentially great fodder for new macro models. So, bringing these constraints into macro models, potentially even building on or using these micro estimates in macro models, there's a lot of material here to work with. And the second is that there are, conversely, just as micro can help macro, there's also, I think, synergies in other direction, right? There's limits to what can be studied by micro approaches alone. And I'll try to be clear about how micro approaches are trying to move towards macro towards the end of the lecture. But I think there's a lot that can be brought to the table through bringing a macro lens. So I think there's a lot of synergies here, and hopefully you see that come through throughout the lecture. So goals for today's class, I will review, admittedly, a very small subset of what is a very extensive and large micro literature on agricultural technology adoption. And if we have time at the end, I'll try to highlight some of the ways that I think macro and micro can speak to each other or build off each other in this area. Let me give one plug for Eleanor Wiseman, who's the TA for this section, who, as Joe mentioned, is here answering your questions via chat. Eleanor is going to hold a session on Wednesday of next week, talking about reviewing questions from this lecture, but also talking about some of the emerging evidence on intermediation in agriculture, which is sort of an adjacent field that is a lot newer, but I think also very ripe for sort of this micro-macro interaction. It's also an area in which Eleanor is a real expert. So I hope you all attend that session. Okay, so quick motivation into why we're focused on agricultural technology adoption. So this is the middle of your agriculture module. I'm sure I don't have to convince you all that agriculture plays a key role in the economy of many developing countries. But it tends to have fairly low productivity. So just as an example of that, agriculture accounts for 64% of the labor force in sub-Saharan Africa, but only 34% of GDP. In Asia, those figures are 43% of labor force, but only 20% of GDP. And just as a point of comparison, in the US, agriculture accounts for about 2% of labor force and 2% of GDP. And so the reason we're focused on agricultural technology adoption is that the lack of adoption of agricultural technologies is seen to play a key role in shaping these patterns, potentially these low productivity numbers. Okay. So what do I mean when I talk about technologies? Well, the literature uses this term quite broadly, so it could apply to things as broad as production practices or post-harvest handling. But the most common thing that people typically mean when they talk about agricultural technologies is these green revolution technologies. So the green revolution was a push in the 1950s and 60s to develop new forms of high yielding varieties of seeds, of inorganic fertilizers, insecticides, pesticides, and irrigation. And these technologies are credited with increasing production worldwide, especially in developing countries. Okay, so Doug has a nice piece recently out in the JP on exactly what is the causal effect of these green revolution technologies on yields, and it seems to be absolutely massive. And this is credited with saving over 1 billion people from starvation. So Norman Borlaug, who is considered the father of the green revolution, received the Nobel Peace Prize for this in the 1970s. It's really sort of one of the great success stories of the past century. But that said, the Green Revolution did not transform agricultural production everywhere. Okay, and this is particularly notable in the sub-Saharan African context. So just to see this, these figures are showing you on the left-hand side cereal yields over the course of 1960 to 2000. And on the right-hand graph, you see fertilizer use from 1960 to 2000. And what you see is in East Asia and the Pacific, right, really rapid growth in yields and rapid adoption of fertilizer. You see Latin America and South Asia being somewhere in the middle, both in terms of yields and fertilizer use. And sub-Saharan Africa really is an outlier here. So very little growth in yields, pretty stagnant over this period, and also very low adoption of fertilizer. So what's going on here? So why would people not adopt these new, seemingly profitable technologies? So there's sort of two big buckets of explanations, and I'll break them down further in just a bit. The first big bucket is that, maybe in fact these technologies are not all that profitable. So yes, they do seem to increase yields, but they also maybe increase cost, right? Both the cost of buying the technology itself, but also in particular thinking about things like complementary labor cost. So many of these technologies require farmers to also put in more labor. When you value that, maybe these technologies are not profitable. And moreover, there's probably variation across farmers, right? So for some farmers, it might be profitable and others not. Tabnit Suri has a really nice piece on this that I put in your syllabus on looking at farmer heterogeneity and how important that is to take into account here. Okay, so it's one sort of set of explanations. The other set of explanations is, maybe these technologies would be profitable in a world with perfect markets, but they're not adopted, at least not adopted universally, because of one or more market inefficiencies. So what do we mean by these market inefficiencies? Well, this categorization comes from a nice review piece by Kelsey Jack. This piece was done, it's a white paper that was done in conjunction with the Agricultural Technology Adoption Initiative, ATAI, which is an initiative out of UC Berkeley, SIGA at UC Berkeley, and JPEL at MIT, and they funded a lot of work in this space. And so this is Jack's sort of taxonomy of market inefficiencies. So one possible inefficiency is externalities. So some technologies may create benefits that spill over to other people. And if farmers aren't internalizing those benefits, they might under-adopt. Of course, you can also have this in the other direction of over-adoption, but we're thinking here mostly about under-adoption. Second, input and output market inefficiencies. So sort of most basically, you can think here about infrastructure, things like roads. You can also think about supply chains and other contracting problems or market power issues along those supply chains, things that are making it more costly for either farmers to purchase inputs or to sell their outputs. There might also be landmark inefficiencies. So in settings where land tenure rights are weak and property rights are weak, farmers might be hesitant to invest in their land because they fear that they'll make an investment and that harvest might be expropriated, and so they choose not to invest. That's one possibility. Labor market inefficiencies. So many of these new technologies, as I mentioned, require complementary labor. It's often also more complicated than just saying more general labor. It often depends on the type of labor, skilled or unskilled. The timing of the labor can matter quite a bit for these agricultural cycles. And so anything that places a restriction on labor mobility or just raises the cost to labor may interfere with adoption of these technologies. Credit market inefficiencies. So many of these technologies, most in fact, require sort of upfront costs for a future benefit. So imagine you're investing in fertilizer, at the beginning of the planting season. The return's only going to come later on at harvest time. So this gap in time gives room for potentially having credit market inefficiencies play a role. So maybe farmers don't have the money up front to make what would otherwise be a profitable investment. Risk market inefficiencies. So many of these technologies are both higher return but higher risk, and most have at least some small risk of loss. And so it might be that if you're in a setting where there's not good insurance markets to offset this risk, that farmers who are risk averse are not willing to adopt these new technologies. And you can imagine this could be particularly true for very poor farmers who are right on the sort of margin of subsistence or not. And then finally, informational inefficiencies. And this can mean something as simple as, farmers don't know if this technology exists. It can also mean not sort of understanding the production function more deeply. So not knowing about the benefits that you're going to face in particular, not knowing how to use the technology effectively. This encompasses sort of a wide range of learning. So these are some of the barriers that can potentially limit technology adoption. And I want to map this to some of the research that's been done in this space recently. So we have pretty good data, I would say, on the last three constraints, on credit market inefficiencies, risk market inefficiencies, and informational inefficiencies. And I'll describe those today as we go through the papers that are on your syllabus. We have relatively less evidence on input and output market inefficiencies. So this has been growing in recent years. And this is part of what Eleanor is going to talk about in her TA session, thinking about the supply chains for both inputs and outputs. And then finally, we have very little evidence on these three remaining categories of inefficiencies, on externalities, land market inefficiencies, and labor market inefficiencies. And I want to note, these are all places that I think macro models can be helpful, but you might imagine for these three in particular, these are things that are both, harder to manipulate experimentally, which is where a lot of the micro evidence comes from. And it's also places where I think bringing in some macro approaches could be particularly useful. So this is just a quick plug for ATAI, which I mentioned before. I've put here their website in case you're interested in learning more. They've funded since it was founded in 2009, they have funded almost 50 evaluations in 15 countries. They've got 100 affiliated researchers working on all these different constraints that I just mentioned. And so if you want to learn more about any one of these constraints and sort of the research that's out there, ATAI is a major fund, and their website has a lot of the work that's been done on there. Okay, so that's on the intro. Let me go over an outline of what we'll discuss today. So we'll start by talking about a model of agricultural technology adoption coming from a review piece by Jeremy Magruder. We'll then talk about those three buckets of inefficiencies where we have pretty good micro evidence, right? So credit and risk inefficiencies, as well as informational inefficiencies. And these are places that I really see, there's good evidence here for macro to build on. And then I'll talk a little bit about where we have sort of less micro evidence, but where macro I think can be particularly helpful. And I'll talk about a piece, one of my papers with Marshall Burke and Ted Miguel on externalities and GE effects. And then if there's time at the end, I'll make a few quick comments on sort of synergies between micro and macro and try to highlight a few papers that have tried to work in this intersection. Yes, is there a question? Okay. So let me dive into this model. I will say, I think maybe for the sake of leaving 15 minutes at the end, I will skim over this model, and then Eleanor, I might ask you to review it in greater detail in your section. But let me give you at least sort of the intuitive flavor of this model. So this model is comes from that review piece that I mentioned, which is again a nice place to look if you're looking for a review of what's been done in the literature so far. This is an extension of the model that's in the paper on your syllabus today, the Karlan et al. Paper. And so this is a model of technology adoption under those three constraints where we have a lot of good evidence. So credit constraints, risk, and imperfect information. So the basic setup of this model is that some input X must be committed before the state of the world S is realized. Okay, and S is going to determine the farmer's return from that input and occurs in probability pi. And so the sort of intuition here is that farmers, again, take that fertilizer example, farmers are going to have to invest in fertilizer at, say, planting time. They're not going to get the return until later on at harvest time. And that return is going to depend on the state of the world. So maybe it's going to depend on whether it's been particularly rainy or dry growing season. And so you can already see again here how credit and risk are going to come into play. So credit, right, you're investing in input up front, you're not getting the return till later on. That's where credit constraints can potentially play a role. And risk because you don't know what state of the world you're going to be in. We're going to add to this incomplete information. So a farmer is also going to be uncertain about how her input choices will perform in each possible state. So we're going to add an additional layer of uncertainty here. So production is now also going to depend on the technological production function that's realized. So again, what's the intuition? Well, farmers, not only do they not know, is it going to be a dry or a rainy growing season, they also don't know, even if it is rainy, how profitable is fertilizer going to be on my particular field in this year. So there's uncertainty there coming from a lack of information as well. So again, I think I'll skip over this for the sake of time to leave time for questions at the end, but hopefully Eleanor can go over this. It's a very simple model in which farmers are picking inputs and the amount to either save or borrow as well. Okay, so let me just go over the implications here sort of intuitively. So the idea here is that credit constraints are going to reduce input usage, right? You might want to invest in fertilizer, but not have that cash up front to do so. Risk is going to reduce input usage. You're going to be less willing to adopt if there's some risk and there's no way to ensure that risk. And you'll notice in this particular model, informational failures are modeled much like risk. So it has a similar implication where information failures might also reduce your investment. So this is just a very basic sort of framework for how to think about these three constraints and how they might limit input usage. Let me now get into the meat of this lecture, which is really about the empirical results on these constraints. So we'll talk first about credit and risk inefficiencies coming from this Karlan et al. Piece. So they're going to focus here actually on two constraints, right? So on credit constraints, which we talked about, many investments might require upfront costs and produce gains later on in time. And they're also going to look at risk. So again, the profitability of many of these technologies depends on a variety of factors that are going to vary. So the weather, the macroeconomic conditions, which might shape the price at which you can sell your output, et cetera. A few things to note. The first is that these risks are mostly aggregate risks and therefore pretty hard to insure informally. So informal insurance means, imagine that Joe and I live in the same village. If my kid is sick, Joe might lend me some money when I'm facing that idiosyncratic shock. I might lend Joe money when his kid gets sick, a month or two from now. And so these are sort of the idiosyncratic shocks that we can help to informally insure. It's very difficult to do this sort of informal insurance for risks that are coming in the aggregate, which is most of the case for agriculture, right? So if I have a bad rainfall on my farm, if Joe's my next door neighbor and he's going to have a bad rainfall as well, we're not going to be able to insure each other. And so it's very difficult to have sort of informal versions of this insurance. And again, as I mentioned before, this is particularly hard for poor farmers, right? Who are right at that margin of subsistence or not. So they're going to study these two constraints in the context of northern Ghana. Just a few quick details on this context. In their setting, the median farmer uses no agricultural input, no chemical inputs, so no fertilizer here is what they mean primarily by chemical inputs. And agriculture is almost exclusively rain-fed. And so what that means is they don't have a ton of irrigation. Things are really rain-fed. The yields are going to be very dependent on, was there enough rainfall exactly when it was necessary during the growing period? And so, there's been sort of previous work here showing that weather shocks translate directly to consumption fluctuations. Okay, so a lot of risk in this environment. So they're going to run a pretty complex 3-year multi-arm RCT. So in year one, they're going to run 2 different interventions. So the first intervention is a cash grant. So they're just going to give farmers cash upfront, and they're going to say, use this however you want. And the idea here is that if farmers are credit constrained, and this is the reason they're not adopting inputs, you've now relaxed this credit constraint. Farmers may now choose to go buy inputs with this cash. The second intervention is a grant of rainfall index insurance. Okay. So let me just describe this rainfall index insurance, or often called weather index insurance. So the most basic insurance product you can imagine for farmers would be a basic insurance that pays out when your harvest fails. Now, the challenge with that model is that's going to bring up issues around moral hazard and adverse selection. So moral hazard, because if you exert less effort on your farm, your crops are more likely to fail and you're more likely to get a payout. And adverse selection, because the farmer may have some asymmetric information about how risky their farm is that the insurer may not know, and you're going to induce in the sort of riskiest farmers into an insurance product. So weather index insurance is a way to try to get around these moral hazard and adverse selection issues. And the way that it works is you make payouts based not on the harvest happening on this particular farmer's plot, but based on the weather reading at weather stations in the area. And the idea here is this is going to reduce moral hazard because your payouts are going to just depend on, did we record bad rainfall at your local weather station? It's not going to, if you exert more or less effort on your farm, it's not going to affect your payouts. And it should reduce adverse selection because the insurer should sort of be able to see the history of rainfall and should have an accurate sense of the risk of payouts for each farmer. It does, however, bring up basis risk, which means it's not always the case that you could have totally not your own fault. You could still have bad yields on your particular farm. And if the weather station, isn't right next to your farm or isn't capturing exactly what's happening on your farm, the weather station might say no payout when really you need a payout that year. So there is some risk to this approach. Okay, but this has been a really exciting new, in and of itself, a new technology, but one that's meant to reduce risk and therefore encourage farmers to invest in other technologies. So they're going to look at grants of this rainfall index insurance. The other thing that's quite nice here is in the first year, they're going to give this insurance as a grant. And the value here is they're going to now be able to observe the effect of essentially removing risk or reducing risk for the full population of farmers. So rather than just seeing, among those who buy it, what is their reduction in risk and getting some local average treatment effect, here their treatment effect in year one is really going to be sort of the global treatment effect. Or the global average treatment effect. Okay, year two, they're going to, and one more thing I should say about this is it's the 2x2 design. So what that means is some farmers get cash, some farmers get insurance, some get both, and some get nothing. Okay, so they've done a 2x2 design here. In year two, they're going to keep the cash grants as a treatment arm, but they're going to now sell rainfall index insurance at randomized prices, ranging from 1/8 to the full actuarially fair price. And that's going to allow them to then estimate the demand curve for this insurance and sort of nicely to measure the local average treatment effect among different populations who select into this product at each price. And then finally, in year three, they're going to continue this insurance pricing experiment. So there's a ton of results from this paper. I'm just going to show you two. The first is on the question about demand for insurance in year two, right? So when they actually offered randomized prices. So one thing to note is that in this particular context, they found that at the actuarially fair price, which is around, I think it's somewhere between 6 and 9 here, they found that 40 to 50% of farmers demand index insurance. This is pretty high compared to the rest of the literature. So there's been sort of a whole sub-literature documenting and then trying to figure out why take-up seems to be much lower in most other contexts. Okay? So there's a lot of work on why farmers don't seem to be adopting this seemingly useful product. Again, sort of a technology question, adoption question in its own right. One of the hypotheses is farmers might not either understand the product, it's pretty complicated, or they might not trust they're going to actually get payouts when they need it. And so here, they're able to document that experience does seem to help. So they find that demand is higher among farmers who either themselves got a payout in year one, or who knew someone in their network who got a payout in year one. Now let's turn to impacts on farm investment, right? The primary outcomes they care about here: when you reduce risk and you reduce credit constraints, do farmers actually invest more in their land? So let's look first at this first row here on insured. So they're going to instrument here for being insured with that varying price. And they're going to find that farmers who are exogenously induced to be insured are going to invest more in land preparation. So this is primarily renting tractors, for example, to prepare your land. They're going to actually cultivate more acres of land. They're going to use more chemical inputs. This is mostly fertilizer. The wage effects are going to be in terms of hiring paid labor and family labor. They're positive, although not statistically significant. And in net, when you add this all up, total cost or total investment in the farm goes up. So it looks pretty clearly like in their context, when you reduce risk, you increase people's farmers' investment in their farm. Capital grants, which are right here, this third row here. Okay? So here we're seeing more mixed evidence. And on the whole, they're going to take this to be basically a null. So, a small positive point estimate on land preparation, but not statistically significant. No effect on the acres cultivated. There is an increase in fertilizer, and this is the one thing that's going to come through for the cash grant folks. But sort of mixed evidence to no effect on labor. And when you add this all up, they're going to find basically a null in total cost. Okay? So their takeaway here is that in their setting, it doesn't look like credit constraints are the major thing, right? So you give people money, they don't seem to be investing a lot more in their farm. And also note the fact that the insurance does produce a bigger investment. For the insurance product, they're not giving money upfront, and people are still able to find a way to invest in their farm. They're still able to find the cash needed to invest. So their takeaway here is risk is really important, maybe credit a little less so, with the exception here of fertilizer. And then let me just say for the interaction term, it's significant for fertilizer and sort of positive, but not significant for a lot of other outcomes. I will also note one other thing, which is if you turn to this last column here, value of harvest, right? So they've increased the investment or the sort of cost put into the farm. Does it actually produce higher returns for farmers? And do those returns exceed the cost? And they actually find no, right? So they find that there's not a statistically significant increase in the value of harvest. And it's certainly not bigger than the total cost. Now, on one hand, this might make you think sort of back to that first bucket of explanations, maybe these investments are just not profitable. But I do want to add sort of two notes of caution here about some of these interpretations, which the authors themselves note in the paper. So the first is that harvests are traditionally very difficult to measure. And you'll find actually a huge number of papers in this overall literature, even when they find impacts on farm investment, find noisy effects on harvest. And so harvests are very difficult to measure. In sort of the real world, farmers are often asked to recall how much they harvest, which is a very difficult thing to remember the exact number. There's been advances made in terms of things like satellite remote sensing that I think are potentially really exciting in this space. And the second thing is labor is just very, very difficult to measure here. So, how do you think about valuing the opportunity cost of family labor? This is sort of a challenge that you'll see throughout this literature. Okay, so this is just one example of, again, a really large literature on credit and risk. I want to just quickly summarize the takeaways from a few other papers, just to give you a sense of the flavor of the findings here overall. So there's been lots of other papers that have tried to give credit rather than cash grants, actually give loans. And what they tend to find is that take-up is pretty far from universal. So in this sort of, a third or less or fewer farmers take up. Fertilizer use does generally go up with credit access. So it seems like for some folks, getting access to credit does encourage them to adopt more agricultural technologies, more fertilizer. but the increase in input usage accounts for only a small fraction of the total loan size. So a lot of the loans are going to something else. It doesn't seem like this is the biggest thing that farmers could possibly invest in with the highest return. It doesn't seem like if you gave loans to everyone, that everyone's going to use the full loans to invest in agricultural technology. So one, I think, balanced perspective on this is it seems like there's a substantial minority of farmers who would consume more inputs if credit constraints were lifted. On the risk side, pretty clearly, it seems like across the board that reducing risk does seem to lead farmers to invest more in inputs and in high risk, high return technologies. But as I mentioned, with the exception of this paper, most other papers tend to find pretty low adoption. Again, potentially because there's trust issues, there's understanding issues. There's a nice paper here on the fact that you have to pay the premium up front to get the return from your insurance later on. So there's time issues as well. One thing that's particularly promising here is there's been some papers, for example, like this MREC paper here, that has looked at, rather than trying to get people to adopt a second technology of weather index insurance to reduce risk to adopt, the first technology, can we just embed lower risk in the first technology? So concretely, what they're doing here is they're looking at flood-resistant rice varieties. So can we actually change the seeds themselves to be less risky? And that seems to be very, very promising. Questions on that before I go on?
Can I ask a question about the value of harvest? So you said it's hard. You said it's hard to measure, and I wonder whether it's measured in terms of quantity or in terms of market price. Because if you measure in terms of market price, then the general equilibrium effect will come in, because if there's a higher harvest, then the price may decrease because of that.
Yeah, absolutely. And we'll talk about one of the papers of mine that actually looks at this exact issue later on. So here they're looking at the values. This does include the price. The price tends to be easier to measure. So it's easier to run market surveys or just ask farmers, what price did you get? In terms of the measurement issues, I was primarily referring to the quantity here of getting the actual quantity that's harvested, and that's where satellite imaging can help. The price, my takeaway is the price is a little easier to measure, especially because you can do your own, if you're going out and collecting your own data, you can collect that yourself directly, but harvests often require farmer recall, and that's where I think a lot of the problems come up.
Thank you.
Yeah, great question. Okay. So let's turn now to informational inefficiencies. So I want to just very briefly discuss sort of a very basic learning model that I think is common to many of these papers that are thinking about learning about the sort of returns to technologies. So again, the constraint here is maybe farmers don't know these technologies are profitable, and that's why they haven't adopted. So the very basic learning model here, think about an agent who's trying to learn about the return to a certain technology, and we're going to call theta star the true return. Now, this agent, this farmer, is going to have some prior theta naught, which is centered around the true value, but has some variance. And we're going to index this variance by, or parameterize this variance by 1 over h naught. So the higher h naught is the more precise that, or the stronger that prior is. In each period, she's going to learn. So she's going to get a signal, which we'll call theta tilde. And again, that's going to be centered around the true value with a variance 1 over HU. So the higher HU is the more precise that signal is. So both the prior and the signal are centered at the right value. The relative precision is HU over H naught. And the agent's going to be updating her beliefs using Bayesian updating. So let's just see sort of what's going to happen. So we can show that the posterior belief, right? So your new belief after you've received the signal, theta tilde, is going to be centered around the weighted average of your signal and your prior. And the weights are going to be how precise were your prior and your signal. Now, after t periods, you can iterate and show that essentially beliefs are going to converge to the true value as t grows. So people will eventually learn the sort of true productivity of this technology, but it's going to take time. Right? And learning is going to be faster depending on, for example, the precision of your signals. I will just note this is one particular example. There are other examples in which even over time, the beliefs don't converge to the true belief. So if you're interested in that, you can look, for example, at this paper by Abhijit Banerjee on herd behavior. But let's take the case where we're going to assume that farmers we'll eventually over time figure out whether these technologies are profitable, but we want to think about what might inhibit or speed up the speed of that learning. So I'm talking about two papers. The first is this bold et al. Paper. So this paper is set in Uganda. And one of the first stylized facts that they document in this paper is it seems like in Uganda, there's substantial variation in input quality. So they run a pretty neat mystery shopper experiment where they have their enumerators pretend to go be actual shoppers at retailers. And they go out and they buy actual fertilizer and hybrid seeds from retailers. And then bold et al. Take those samples to a lab and test them. And so what they found was that 30% of the nutrients were missing in their samples of fertilizer, and less than 50% of their hybrid seeds were authentic. So really high rates of either intentional or unintentional adulteration, or just depreciation of the quality of these seeds over time. I should note, by the way, this particular finding about the really high rates of inauthentic inputs is higher than or more problematic in this setting than they found in other settings. There's been attempts to look at this in Tanzania and some other locations, and they haven't found as high rates of adulteration. But in this setting, it seems to be quite important. So really high variation in input quality, but interestingly, not much variation in price. Okay. So it looks like, this is not the case of having some differentiated product where the high quality is selling for a high price and the low quality for a low price. Really, across the quality distribution, there's just sort of a single price for these inputs. And so this suggests that consumers maybe can't fully observe the quality of what they're purchasing, right? They're not able to demand a lower price for lower quality, for example. The second step in this paper is that bold et al. Run agronomic trials where they actually have plots of land and they apply to it the authentic seeds and authentic fertilizer. And they have other plots where they use the sort of market level, partially inauthentic seeds and fertilizer. And they confirm that the returns to authentic input, surprise, surprise, are much higher, but they actually have quantitative estimates of how much higher the authentic returns are. I should note, even the market rates, while there's still positive returns to using these inputs they find, but they're much higher for authentic inputs. And so you'll want to ask, how can farmers start learning about which inputs are authentic, right? And then they can adopt those inputs, and that might be really profitable for them. So what are the challenges here to farmers distinguishing between authentic and inauthentic inputs? So they note here farmers an inference problem that the farmers are facing. And I want to note this is true for separating authentic and inauthentic inputs. It's also true in general as an inference problem for farmers learning about the profitability of some technology. And the inference problem is that yields are going to vary due to a number of factors other than just the quality of the inputs. So they might find that at the end of the harvest that their harvest failed. And they don't know, is that because my inputs were inauthentic, or because the weather was bad, or for some reason my soil wasn't as good this year. A lot of other things are changing, things that are either unobservable or observable, but the farmer doesn't know the exact production function. And so it's hard for the farmer to attribute, was this happening because my inputs were not authentic, or because of some other factor. So they develop a really nice Bayesian learning model, which they're going to calibrate using moments from their experiments and their data collection, which is particularly nice. So this is the result of their model. There's a lot going on in this figure, so let me break this down. So on the y-axis here, they're showing the log odds ratio in favor of the profit of the fertilizer being unprofitable. So a log odds ratio of 0 means you're sort of on the fence. You're 50-50 about whether this fertilizer that you're using is profitable. And higher than that means your best guess is the fertilizer is unprofitable for you. And lower than that means you think the fertilizer probably is profitable. Okay, so 0 is sort of that 50-50 point. They're showing this as a function of the dilution rate of fertilizer. So a dilution rate of 1 means basically it's a totally fake fertilizer. Nothing's real. And a dilution rate of 0 means there's no dilution, it's totally authentic. Okay, so this is sort of good quality to bad quality. And they find in their agronomic trials that as long as the dilution rate is less than equal to, I think it's around 35%, I mean 38%, as long as the dilution rate is less than that, then they find in their trials, this is all profitable fertilizer. Okay. So they want to ask, what are farmers' beliefs about whether or not it's profitable, depending on the dilution rate and depending on how many times they've tried to use this fertilizer. So how fast is the learning? So what these lines are showing you, this dark black line is showing you farmers' posterior beliefs after one harvest round. So after they've had one experience with the fertilizer. This long dash line is showing you after 5 harvests, so 5 rounds of experience with fertilizer, and after 10 harvests. So how quickly are they learning? So a couple takeaways here. So note that from a dilution rate of 0.5 to 1, so the really terrible fertilizer that's been really diluted, there's strong learning here, right? So even after one round of trying, one round of harvest, farmers are still above 0 in terms of their posterior log odds ratio. They're pretty sure it's unprofitable. So they can detect really bad fertilizer pretty quickly. This is why you might imagine firms have a strong incentive to not totally dilute, right? Farmers can quickly pick that up. Here in moderate learning, though, here in the 0 to 1.8 or so, right? This is called moderate learning. So this is the really good stuff, right? This is the really good fertilizer that's been barely, if at all, diluted. And still you see here only moderate learning. So it does take a while for the really good stuff for farmers to figure out that what they're working with is the really good stuff, right? So even after one harvest, their best guess is it still is probably not profitable. And it takes somewhere between 1 and 5 rounds of trying to figure out that actually this is profitable for them to get below 0. Now, what's particularly concerning is this area here of weak learning, right? This is right around that switching point of it actually being profitable or not. And you see it takes a really long time for farmers to figure that out. So everything sort of in this range over here below, I think it was 38%, is actually profitable in their studies, but it takes a really long time for farmers to figure that out. So even after 10 harvests, this dotted line here, we're still above 0, right? Farmers' best guess is it's still unprofitable to use. So there's really slow learning here when the actual quality of fertilizer is not so far off from that tipping point of being profitable. And so you'll want to ask, for the actual fertilizer available in the market, where does it lie in terms of these different buckets? And most is here in this weak learning bucket. Okay, so 60% of the samples are here in this learning, in this weak learning range. So this is sort of an explanation behind why it's difficult for farmers to observe the quality and to learn about the quality of what they're growing with, right? And that might be one of the reasons that they're very slow to adopt. Now,
quick
this speed of learning
on the last
please.
slide, on the one prior to this. So is it the case that these 3 lines do not intersect at the kind of switching point between profitability and unprofitability, or because that's what seems intuitive to me at least, but is it the case that they actually intersect lower than that?
Yeah, they're intersecting lower than that. So the cutoff here is 0.338. So one thing that's important for this model is thinking about people's priors. So people, and you can make different assumptions about people's priors. So they're going to assume that people's priors are evenly distributed 0 to 1, uniformly distributed 0 to 1. And so, but the actual level that's profitable is 0.38. So that's why, for example, even after one trial, even after one harvest time, people think it's probably not profitable. It's because their prior is centered around, 0.5, for example, and the true value is 0.38. You could think about having different distributions there. So I don't think there's any mathematical reason about why these should cross at certain rates here, because I wonder what would happen if you had the distribution actually be centered at the true value, or so the true profitable value. But yeah, there's no reason why these things have to cross at any particular point. Other questions on this? Okay. So this whole model, though, is talking about sort of how long can take you to learn. So, even at 10 harvests, you still might not know. That can be a very long time if you're thinking about only learning from your own experience. But there's a thought that potentially we could speed up this learning process for this case and for other technologies if you can learn from your peers. So this is really this idea of peer learning, potentially speeding up the learning process, has been a big motivating factor behind some of the models that are common to see in extension services worldwide. So extension services or extension agents are people who are hired by the government to go out to the community and try to disseminate or share information about, say, new technologies or planting processes. And one of the models that many, especially developing country governments employ, is that of lead or seed farmers, they call them. And the idea here is extension agents will go out and they'll pick a prominent person in the community, and they will dub them to be the lead or the seed farmer. And they will give that seed farmer the technology. They will set up a demo plot with that seed farmer. And the goal is that seed farmer, once trained, will then go out and disseminate that knowledge to their peers and to try to kickstart this sort of peer learning process. And this paper by Beaman et al. Is going to ask, how do we pick those seed farmers? And is there a way to use targeting, or in their case, network theory, to more optimally pick these seed farmers and speed up peer learning? So if we're thinking about peer learning, how do we sort of optimally seed this network? So they're going to take seriously two different models of contagion, or in this case, sort of technology diffusion. So the first model they're going to consider is one of simple contagion. And in this model, an agent's going to adopt as long as one of her peers adopts. So I think of this as being the case where maybe you don't know a technology exists, and all you need to do is hear it once from one person, and then you'll think, oh, great idea, let me go do this. Complex contagion is when an agent's going to adopt as long as lambda of their peers adopt, and typically lambda is greater than or equal to 2. Right? So this is the case where you have to see multiple of your peers adopt before you're willing to. And I think that this is the case more where, farmers might not know, well, how profitable what are the returns to this new technology? I'd like to see multiple of my peers give it a go before I'm willing to actually dive in. So what are the implications of these two models of contagion? Well, imagine that you are running an extension service, and you're thinking about training up 2 seed farmers in every network, let's say every village. Who you're going to pick, the optimal entry points, are going to depend on which contagion model is accurately describing how diffusion happens. So in a simple model, the simple contagion model, if you had 2 seeds, you put the first seed in the dense part of the network, right? You want them to reach sort of the most people. But the second seed, you wouldn't bother putting that second seed right on top of the first, right? Those people who are connected to that first seed are already going to adopt. You want to put that second seed further out in the network to get to other people who are in the more distant periphery of the network. However, if complex contagion is the right model here, then you want to choose both seeds in the central part of the network, right? Because those people are going to really need to see at least 2 people adopt in order to be willing to adopt themselves. So this is going to change who you would pick optimally in terms of how to seed. So they're going to apply these 2 different models of contagion to a context in Malawi. So looking at the adoption of a pit planting technology. So this is basically, it's a very simple technology. It's just changes how you plant. You basically create a little divot or hole and you put the seed into it, and that can capture rainfall and other nutrients better than just scattering the seeds on the ground. This is a very common planting approach in West Africa, but it was new to East Africa. It hadn't been used there before. So look at the spread of this new technology. One really nice feature of this paper is they're going to collect complete network data in 200 villages. Now, this is incredibly expensive and costly. They're going to go to each individual person and they're going to ask, who do you talk to about agricultural decision making? And they're going to get the full network data. Then, because they have this full network data, they can then simulate various models of, well, who in this network would you pick under simple contagion? Who would you pick under complex, for example? And then they're going to randomize those villages into actually picking based on different models, right? So some villages are going to get their seed farmers who are selected via simple contagion, some via complex contagion. But also the third arm I think is particularly nice, which is kind of acknowledging that in reality, collecting complete network data, while very useful for an academic study, is not feasible in terms of at-scale implementation. So we don't expect the government of Malawi to go out and do full network surveys in all villages. And so what might they do as sort of a rough proxy? They might look at geographically where are people located and assume that folks who are located in kind of dense parts of the village geographically are in dense parts of the network. Okay. So the third thing they're going to do is basically pick via complex contagion, but using the geographic network as a proxy for the actual underlying network. And then they're going to compare all these to a control, which is going to be selection made via status quo, in which the extension officers just pick who they think are the best seed farmers. So just to show you, this really changes who they pick as seed farmers. So these are just 3 examples. Let me show you just one here in village number 288. So you see here for the simple contagion module, which is our model, which is here in green, they've picked the first seed, again, right in the middle of the network. The next optimal second seed is going to be out here, right? These folks are all getting hit by this first guy. And so you want to try to reach some of these folks who are out in the periphery with this guy here in green. However, if you want to apply a complex model, then you're much better off picking both folks in the center of the network, because no one's going to adopt unless they see 2 or more people adopting. And there's some overlap, but it's nice because they can actually say counterfactually who would have been picked in every location because they have the full network data. There's a bunch of results again. I'm just going to show you 2. The first is looking at an individual level on diffusion within the village. And so what they're going to find is that both in terms of whether you've heard of pit planting, whether you know how to pit plant, and whether you actually adopt pit planting, being connected to one seed doesn't seem to change your knowledge of or your adoption of pit planting. It's really being connected to 2 seeds that makes the big difference here. Okay, so you're really seeing increases in both knowledge and ultimately adoption when you're connected to 2 seeds. So it looks like this is evidence that that complex contagion model is probably the right one to describe how information is diffusing in this network. One thing just to note, a really important thing to do here, and they note this in their footnote 3, is whenever you're looking at sort of connections to, say, treated individuals, you want to control for underlying network, right? So you want to say, you don't want to compare people who are in the center of an area to people who are in the periphery. They're going to have different connections to seeds, but also be different in a bunch of ways, right? So they're going to control for all the underlying network characteristics and then say, based on the randomization, did you randomly happen to be connected to a seed, controlling for kind of all of your connections more generally. Okay, so they're using just that treatment-induced exogenous variation. Okay, so it looks like complex contagion is the right way to, or sort of the right model here. And so is it the case that in villages, now we're turning to village level regressions, in villages where they ran the complex contagion, do you see more adoption than in villages where they picked seed farmers based on simple contagion? And it seems that that's the case. So it looks like, especially on the extensive margin of do you have any non-seed adopters, here it looks like the complex contagion model really does a lot better than the status quo. Okay, so it's a lot better at getting at least some people in the village to adopt. Simple seems to do better than a status quo of having extension agents pick, but not quite as well as complex. And then finally, geographic is sort of similar, where it's not a perfect substitute for having full network data, which is, I think, disappointing when you think about how this would be scaled, right? It's not as good to just say, let's proxy for the network based on people's location, but it does seem to do a little bit better than the status quo of having the extension agent pick. So this is all to say, you know, if we can take seriously some of these network theories, can we do a better job at speeding up the knowledge diffusion process, right? By how we pick these seed farmers. Okay, so there's a lot more on info constraints. I think for the sake of time, I'll skip over this, but just to say, you know, there's a lot of work out there, and I really encourage you all to take a look at this. Okay. Let me now, in the remaining time, talk about this last paper on externalities and GE effects. And this is a place where we have relatively less micro evidence, but it's a place where I really think that macro can help. So this is a paper of mine joint with Marshall Burke and Ted Miguel. So the context of our paper is looking at this trend that's common in East Africa, which I'm showing to you here, but really across the developing world, which is that there tend to be fairly large and fairly regular fluctuations in the price for staple commodities over the course of the season. So this is showing you major markets from East Africa. And what you see here is the price over the course of the season, with this blue box showing you the timing of harvest. In this case, we're looking at maize. So what you see here is that really sort of across the board, what's happening is right after harvest, prices are dropping pretty precipitously. Only to increase and rise as you go into what's often called the lean season, when prices are high again, and then they fall the following harvest. So there's a cycle of falling prices right after harvest and growing over time. So in major markets, these price fluctuations are pretty large. They're about 25 to 40% in major markets. They tend to be much larger in more rural areas. So for example, in our study site, which is here in Western Kenya, the price fluctuations over the time period that we were doing the study, which is about 4 years, ranged from 40% to 125%. So really large fluctuations in price over the seasons. This is a point of comparison in US corn markets, right? The price fluctuation is more like 5%. So much larger fluctuations in developing countries. Okay, so we've established that staple food prices are not fixed within the season. Now, one important thing to know is these staple foods are storable, right? So storable should allow the movement of grain intertemporally. And sort of in the simplest model, an unconstrained intertemporal profit maximizer should store a unit of grain if the discounted expected future price is greater than the price today plus the cost of storage. So you might think that farming households should be using storage to buy at a low price and sell at a high price. Instead, it looks like they're doing the exact opposite. So this is data from our pilot. And what you see is that farming households appear to be either selling low at harvest time or buying back at a high price later in the season. And often they're doing both. So many farming households will essentially sell right after harvest time at a low price. They'll run out of their inventories, and then they'll return to the market to buy back at a high price later on in the season. And so again, this data here is showing you that inventories in the weeks post-harvest are rapidly depleted. So this is the mean and median farmer. And so what you see here is the median farmer runs out of their own inventories by about 20 weeks post-harvest. We can also look at the quantities sold minus quantities purchased, and you see that farmers are selling, primarily selling in this post-harvest period, and actually buying back later on in the lean season. So they're selling when prices are low, and they're buying back when prices are high. This really matters when it comes to welfare. So the modal household in our sample is giving up about 1 to 2 months of agricultural wages by selling low and buying high instead of the reverse. Okay, so what's going on here? Why are farmers not using storage to arbitrage these price fluctuations? So we did a lot of focus group work with these farmers prior to running this intervention. And the most common answer by far across the board that we got from farmers is that they're credit constrained. So as farmers say, they know they could make more money by waiting till later in the season to sell, but they have a lot of bills that come due at harvest time. So in particular, school fees are due right after harvest. And the issue here is they don't have access to other sources of finance to pay, for example, those school fees. And that's going to then tie together in time the timing of expenditure needs and sales. Right? So these high harvest time expenditure needs have to be funded by high harvest time sales if there aren't financial markets that allow them to move across time, move money across time. So that's the hypothesis coming from these focus groups. We're going to test this by offering a harvest time loan to smallholder farmers worth about $100. Now, what's particularly key here is we're going to randomize this at 2 different levels. So we are going to do the basic thing, which is randomizing the loan offer across farmers. And that's going to allow us to look at outcomes on things like inventories and net revenues and consumption. We're also going to randomize the density of treatment. Okay, so in some areas, we're going to randomly treat more farmers than in other areas. And that's going to allow us to look at outcomes on things like market level prices. And I'll describe that experimental design in a little more detail in just one slide. We'll have 3 rounds of data. So we collect really high frequency data. This is a context in which the timing of things really matters. So we'll have 3 rounds of household surveys throughout the year. And we collect on a monthly basis price data at 52 local markets. We ran this intervention for 2 years. So we ran it for 1 year. It seemed promising. We went back and re-randomized and ran it again to get a replication analysis embedded here. And then we also ran a long run follow-up survey 1 to 2 years after the loan ended. So a little more on this experimental design. So this is what's known as a randomized saturation design. And there's a couple ways to do it, but here's how we did it. So we took our entire study area and looked at the sublocation level, which is an administrative district in Kenya that accounts for maybe 5 or so villages. And we randomized those sublocations into high intensity and low intensity. And then in the high intensity sublocations, we sampled 80% of farmers, and in low intensity, just 40%. Then within those groups, we then randomized into treatment and control. And so as a result of this design, we're going to have double the number of treated farmers in the high intensity as we have in the low. So this is becoming a new and growing sort of approach within the micro literature to think about estimating GE effects experimentally. So we're going to be able to ask what happens when more people are treated, what happens to, for example, market prices. So let me first, before I show you market prices, let me first show you what happens to at an individual level, just comparing basic treatment control farmers. So this is showing you across the season. So November, December is sort of that immediate post-harvest period. June, July, August is the lean season when prices are quite high. And so what you see here in black is the point estimate on the treatment effect and the 90 and 95% confidence intervals. So you see that treated farmers are storing more, they have higher inventories, basically all the way out until the lean season starts, and then they start selling off their inventories. In terms of net revenues are initially actually lower for our treated guys, or our treated farmers. That's because they're holding back on selling to the market, right? So they actually have lower net revenues at first. A few people are actually buying with their loan. And then later on in the season, they're releasing that stored maize and at a higher price, and so their revenues go up. And I'll show you in a moment, when you add all this up, you get a very strongly positive total effect on revenues. Household consumption, we see similar patterns, but it's not going to be statistically significant. Sort of like harvest levels, consumption is often also quite difficult to measure with precision. Okay, so this is showing you at an individual level the results. So we look at results broken down by those 3 rounds of surveys, so you can see what's happening over time. But let's, I think, for the sake of time, just focus here on the overall effects. So consistent with what we saw in the previous graph, overall inventories go up, overall revenues go up, and consumption goes up, though again, not quite statistically significantly so. Okay, so it looks like this intervention works to encourage farmers to store more, and as a result, they earn higher revenues. Now, what's happening at a market level? So by encouraging greater storage, this loan is essentially shifting supply at different points in the season. And so we want to ask, does this affect local market prices? So what should we expect to happen here? Well, when more individuals are storing or engaging in arbitrage, we would predict that prices will be higher immediately post-harvest, right? This is when prices are typically low. So they'll be higher immediately post-harvest as maize is in stores rather than on the market, and lower later on as that stored maize is released. Okay, so higher post-harvest, lower later on. And that's in fact exactly what we see. Okay, so in this post-harvest period, prices are significantly higher in those high intensity locations, and they're lower later on in the lean season, though this is not statistically significant. So it looks like there is an effect on local market prices. Just to note, one thing that we don't go into in this paper, but I think would be a great place for either a macro model or a trade model to think about is, what does this imply about how integrated these markets are? So we're really shifting supply at a very local level, and we're seeing a local price response. That to me indicates these markets are not terribly well integrated. And I think you could think about applying models to think about what are you learning about the kind of degree of integration of these markets based on the local price response to local supply shocks. Okay, finally, we turn to this question of externalities, right? So this is why I put this in the externality bucket. So what do these GE effects mean for the individual returns to the loan? So just to summarize where we're at, this loan is designed to enable farmers to arbitrage these seasonal price fluctuations. High density areas are seeing significantly higher post-harvest prices and weekly lower lean season prices. So we've sort of diminished that gap you typically see in prices. And so by diminishing that gap in prices, we may be diminishing the profitability of storage, right? We've reduced sort of this arbitrage opportunity, and that might reduce the benefit to those who are treated. Now note that, this might reduce the benefit to treated individuals, but for untreated individuals, right, folks who aren't storing, this might be a beneficial thing, right? So the folks who are still selling at harvest time are now getting a higher price, and the folks who are buying back in the lean season are now able to buy at a lower price. Okay? So it's changing the distribution of those benefits. So we're going to explore this using the following specification. We're going to regress those 3 main outcomes on inventories, revenues, and consumption on a dummy for treatment, a dummy for being in a high intensity sublocation, and the interaction term. And so now beta 1 is giving you the treatment effect for treated individuals in low intensity areas, right? Folks who don't have many people around them who are also storing. Beta 1 plus beta 3 is giving you the treatment effect for treated individuals in high intensity areas, right, where many people around them are also engaging in arbitrage. And beta 2 is going to give you if there are any spillovers to untreated individuals who are located in high intensity areas. So here's what we find. So let's focus on this net revenue column 2. So the treatment effect for treated individuals in high intensity areas is really, in low intensity areas is really large, much larger than we found before in the pooled specification. Okay, so a lot of these benefits that we found overall are really concentrated among treated individuals in low intensity areas where not many people around them are storing. In contrast, for treated individuals in high intensity areas, right, for them you have to add up beta 1 and beta 3. Right? For them, the effect is still positive, but it's much smaller and it's no longer statistically significant. So it looks like these gains are really much larger when you're thinking about folks who are in these low intensity areas where not many people around them are storing. The gains seem to be eroding when other people around them are engaging arbitrage too. And then finally, this is not statistically significant, but suggestive there might be some small gains to untreated individuals in high intensity areas. So the takeaways here are, these revenue effects are concentrated among low intensity individuals. The takeaway here is that arbitrage is most profitable when you're the only one doing it. When others start engaging in this, this is going to erode the profitability of you engaging in arbitrage. Methodologically, one of the contributions of this paper is just to note that the impacts that are captured in small pilots might not correspond to impacts at scale. So note that if we had just estimated this intervention among the low intensity folks, right, we would have really sort of overestimated the benefits that you would probably see if you scaled this up to most farmers in the area. So we would have said, hey, this is fantastic for net revenues. This is going to really benefit the borrowers. When in reality, at scale, borrowers are seeing much lower gains, still positive, but much lower. That said, there are potentially the spillover gains to others. And so we try to think about what these GE effects mean for the distribution of gains. Right? So these small, potentially indirect gains per person, we do a very small model to show this can be a large part of the total gains. And in this context, it looks like high saturation, so sort of scaling up these loans, does provide larger social gains from smoother prices, but the gains to the actual borrowers themselves are lower. Okay, so lower private gains, and that might explain some of the under adoption. Okay, so let me, any questions about that before I go on?
Hello.
Yeah.
I was just thinking maybe if you looked at the effects of maybe risk preferences of people and how that influences whether they store their harvest or they sell it.
Yeah, it's a great question because, so just to flesh that out, because it's a really great question. So prices rise on average over time, but there is some variability across years, and farmers don't know exactly by how much prices are going to rise. So there's uncertainty. You can think of storage itself as the technology, right? There's uncertainty about the returns to storage. And so we did look at that. We do have measures of, the typical way you often ask about risk preferences in these surveys is you run a module where you say, would you take X amount for sure, or a lottery in which you get, Y for 50%, 50% you get Y and 50% you get 0. And you can kind of measure people's risk aversion by changing those X and those Y terms. We don't find any correlation between people storing and risk preferences. I have to say, I'm not totally convinced that these questions are doing a really good job of capturing kind of real risk preferences. And so I think improvements in doing that, whether it's by having, these are all hypothetical too. So having kind of real estate questions, looking at how people choose to take risks in their actual real life, all those things would be, I think, valuable methodological improvements to how we capture this. And then you might see a stronger correlation. But I will say, if you're interested in this topic in particular, Hope Michelson has a nice review piece looking at variability in these seasonal price fluctuations. And she shows that there's, a minority, but a substantial minority of sort of seasons and years where prices don't rise. And so this is a risky, albeit on average, profitable investment. Great question. Other questions? Okay, so let me, in my final 5 minutes, just quickly make a few comments on this potential synergies between micro and macro, and just highlight very briefly a few papers that are trying to do this in the agricultural space. So this is a review piece by Joe that I just absolutely love and really encourage folks to take a look at. Joe and co-authors, entitled From Micro to Macro. I'll try to summarize. Joe, please correct me if I'm getting any of this wrong, but this is also sort of, my take on things as well. So the sort of premise of this review piece is that, each micro and macro, they each had their strengths, right? So micro has undergone this, causality revolution in which, especially through RCTs, in which we've gotten really nicely sort of well-identified causal estimates of program effects, estimates of different important economic parameters coming from RCTs. And from micro literature tends to be pretty deeply grounded in kind of the reality and the data of developing countries. So doing a lot of field work, having a lot of rich admin micro data, really sort of grounded in what's going on. On the other hand, macro, their strength is really thinking about kind of the big picture questions, right? So what are policies that have an aggregate or economy-wide effect on welfare? So those are the strengths. And then the common, though I'll be very clear, not inherent critiques of these literatures are, micro often is not focused enough thinking about, what would the aggregate effects at scale be? What's going to happen in general equilibrium when other things adjust? A common critique, again, not inherent, but common, is it's disconnected from theory. And from the macro side, again, common though not inherent critique is it's relying on very strong structural assumptions, often employing calibrated parameters that might be either not well identified, period, or maybe are well identified but not kind of from the local context. And so you can imagine, the strengths of one are sort of the weakness of the other, and you can see how these two things can really start to complement each other. And there's been movements in macro that maybe you're discussing in this course, sort of moving towards incorporating, heterogeneity and other factors that make it tie a little more easily to the micro data. I do want to highlight here from the micro side, kind of moving towards the macro, there's been an improvement in methodological tools that are helping to bridge this gap. So we just saw one on randomized saturation. So how can we experimentally, in a well-identified way, estimate these GE effects, for example, or local effects on prices? There's also been attempts to do randomization at scale. So again, one of the critiques is that many of these micro evaluations are often implemented in small scale. We saw an example of where the effects at scale might be different. There's been approaches to even just do the RCT fully at scale. So there's been, evaluations in which entire programs are randomized across, the entire state in India, for example. And then finally, there's been sort of this merging between taking, say calibrated or estimated parameters from RCTs or natural experiments and embedding them into structural models. So trying to learn more from these RCTs or natural experiments. And so I won't probably have time to go over all of these, but there's been, I think, a lot of work in this kind of merging of micro and macro coming from the agricultural technology adoption literature. So the piece that we just mentioned on storage loans, there's been kind of a similar piece by Gunther Fink and Kelsey Jack and others looking at offering seasonal loans to farmers and seeing how labor responds and shifts around and how that affects local labor market wages. Work on thinking about bridge access and market access and how that affects market choice. Julieta and Namrata had this nice piece in which they are looking at farmer mechanization and how that affects labor demand. And they've actually basically randomly subsidized people to adopt, I think it's tractors in their case, or some sort of mechanization. And they're seeing how that affects labor demand. And Lorenzo Casaburi and Jack Willis are randomizing subsidies to farmers in Kenya to rent out their land to look at frictions in land markets. And I have another paper looking sort of generally at how agricultural policies might look at scale, using existing RCT estimates and trying to embed that in a GE model to think about how, when you scale up policies and output and input prices change, what that means for changing average and distributional effects. So sort of a growing literature here. You see most of these are dated pretty recently in sort of this agricultural technology space. And I just want to encourage folks, there's, I think, a lot of room here to do some exciting merging of micro and macro. And we'd love to list your paper next. So let me, it's 12:15. Let me stop there, Joe, and see if there are questions from the room.
Thanks. Do we have questions from the front row? I have a ton of questions.
I have a question. So on kind of the timing of liquidity constraints in agricultural markets. So in your paper, right, you're relieving a liquidity constraint after the harvest, kind of immediately post-harvest. Other cases, right, you might think you want to give out credit before planting, which is when people can invest in agriculture. In the Think et al. Paper, right, that you have here, they're relieving liquidity constraints during the lean season. And I can imagine, so actually in most of these cases, if it's credit, right, you're relieving liquidity in one location, but you're actually going to like force them to repay the loan in a different time, right? And so you could even imagine that like a loan at planting time, right, that lets people purchase fertilizer, it exacerbates the problem that you highlight in your paper if they have to repay the loan post-harvest. So in your view, right, is there kind of an optimal timing of credit, or you know, how do the results in those papers conflict with each other? Does that kind of make sense?
Yeah, no, it's a great question to think about, kind of mapping out the full over the season, the full distribution of kind of the input of when cash is coming in and when expenditures are going out. And Kelsey and I have actually talked about doing something like that sort of with our two papers. So yeah, it is a challenge. So I would say actually, so yes, I agree that actually some of these loans, if they're then coming due at harvest time, can really be a problem. And in fact, there was an effort, for example, by the Malawian government. Brian Dillon has a paper on this, in which they intentionally moved the timing of school fees closer to harvest, with the goal of making it easier for farmers to actually pay school fees, moving it to the same time as harvest. And Brian Dillon actually finds that this exacerbates the storage problem that I'm mentioning here. And so farmers all sell at harvest, and it's basically making everyone sell at the same time. And so they're all getting a lower return because supply is sort of flooded on the market. So I think the challenge here is figuring out first kind of what is the life cycle of when expenditures and income happen. And then also thinking about, is there a way to think with the GE effects and not have everyone do things at the exact same time? So that's really the problem here, is that everyone has school fees at the same time. A lot of bills come due at the same time. If you could spread those out, that would probably be most beneficial. And so actually our loan is not due at a particular time. So farmers have flexibility to repay at any point over the next year. And so they can choose the timing of when they're going to repay. So we're not forcing them to repay, for example, at planting time, which might be harmful if they're trying to invest at that point in inputs. So I think in general, just more flexibility and disconnection of the timing of expenditures and income would be useful. And having an eye towards the fact that for any of these things that are going to be aggregate shocks, like for example, school fees, where everyone has to pay at the same time, that could induce aggregate supply decisions that have effects on local market prices.
Thanks. I guess one more question then, if no one else in the row has it. So do you think there needs to be higher kind of standards for RCTs to be used in calibrating macro models like this? I mean, specifically maybe around standard errors. So like, I think most RCTs are kind of barely powered, or at least a lot of them are kind of barely powered to reject zero, right? But not necessarily be super informative about the exact point estimate. Like, how do you account for, say, if you have an RCT estimate, like it's centered at 10, but it could be 1, it could be 19, right?
Yeah.
Can you still use that?
Yeah, it's a great question. Oh, and I'm getting a notice that my internet connection is unstable. Can you all hear me okay? Yeah, okay. Yeah, so this is a great question. And I should say, I think this is an important critique or concern. And I don't think it's specific to using these in models. So I hear you, which is, if you're estimating, certain parameters, you care about the magnitude, not just that it's distinct from zero. I think that should be true in RCTs in general. So imagine you have kind of the most basic, totally just policy oriented. You just want to know, does this thing work? You want to compare that probably to the cost of the program. And so you want to know, not just does it produce any benefits, but what is this exact size of the benefits, and do they justify the cost? And is this for the cost, is it the biggest benefit relative to others? So I think, there should be more of an interest in thinking about the magnitude in general and not just distinguishing from zero. But I hear you. I think it's particularly important if you want to think about, bringing this into a model. I think there's other things to think about too. So for example, the time duration of changes. So a lot of these RCTs are also fairly short run. And so when you think about, for example, key elasticities you might want to bring into a model, do you mean a short run elasticity, or do you mean a long run elasticity? And many of these models are assuming, unless they're sort of intentionally dynamic models, many of these models are thinking about kind of long run changes, or ways that people are responding to things. Many of these RCTs only run for a year or two. And so if you think there's transition costs, are you getting sort of the full effect within that time period? And there's been, pushes on that to try to, for example, do longer run RCTs. But a lot of ways in which I think, I think thinking about putting them into models would help to raise these issues more clearly. And I think these are issues that should be relevant even to folks who are just caring about kind of basic impact evaluation, totally on a micro level anyway. And so I think, these kind of questions are really crucial, and could be pushing forward these questions could be a nice side benefit from the merging of these two literatures. Please.
Okay, can you hear me?
Yes.
Okay, I've got a little challenge with RCTs basically, because I think they tend to undermine macro problems. I mean, some macroeconomic challenges under which many of under which they carry out the experiment. That's number one. And I'll also have a challenge with the scalability of the output of such studies basically. I mean, if I go to a rural farm in Malawi and I do a simple experiment and I give $100 and things like that, I definitely will observe certain effect. But that's not taken into consideration. Look, for agricultural output, basically, I would have imagined that the role of the government in taking up excess output of the farmers as a way of providing some form of storage facilities where the government takes up excess produce from the market, thereby stabilizing the price in the market and things like that. And what about the demand side of the purchasing power of the people to also be able to compete in that market? I mean, so some of the studies, honestly, they leave me more confused than. So I don't know, how do we address such problem?
Yeah. So great questions. Let me take I think two branches of your comments, which are both fantastic. So one is sort of the limits of thinking about what are you learning in an RCT and how might that be different from the actual impact of the policy at scale. And so there's a nice review piece by Karthik Muralidharan and Paul Niehaus and maybe others, looking at how things can change at scale. And they have kind of three main factors they're worried about things changing at scale. So one is the issue you raised, I think, about implementation. So people might respond differently if there's sort of a researcher coming in and offering a program. The other critique that's often brought up that's very similar is, the types of NGOs, for example, or even the types of governments that we as researchers choose to work with for these RCTs are typically some of sort of the, you're only going to run this RCT if you feel like the NGO you're working with is implementing the program properly, has the time and the managerial capacity to work with you on randomization, understands randomization, all that. And so there's a select group of NGOs or even governments that are willing to work with you on these RCTs. And so we're getting evidence from maybe the best NGOs. What would this look like if it were scaled up by other NGOs or different governments? So implementation can be quite different at scale. And the two other things which you didn't mention, but I think are worth highlighting is, one, many of these micro studies are done in one particular area. And so there can be heterogeneity in treatment effects where your results from one area might not apply to other areas. Again, this is where a place where I think if you have a model of, what explains that heterogeneity, and if you can sort of explain the heterogeneity within your study area, you might be able to apply that to other areas to predict how those effects would change. And the third kind of camp is GE effects, thinking about, for example, changing input or output prices or other shifts that happen. This is where I think some of these randomized saturation designs can be quite useful for trying to estimate these effects locally. And then you might want to embed that, for example, in a GE model. So that's on scaling. So there has been, I think people are taking really seriously some of these concerns you're raising and are trying to move towards that, both in sort of qualitatively talking about how these can be different and then trying to quantitatively develop tools that can address these. The first issue about undermining is really important. And again, this is where I think you're right that the micro literature is often focused on solving one problem and not thinking about kind of, are we creating new problems in other areas or how do these problems interact? In particular for storage, so I will just say with that particular example, so again, we work here in Kenya, and the National Cereals and Produce Board in Kenya does do some storage for the purpose of stabilization that you're mentioning. It's not been terribly successful, so you still see prices fluctuating quite a bit over the season. And they've personally had issues around, just sort of management issues and corruption issues and a bunch of issues over time. So it hasn't been terribly successful, but there certainly could be a role for that. And you're right, this is really kind of going to the micro level of why aren't farmers storing. You might ask an intermediate question of why aren't traders or intermediaries storing who don't have these kind of credit constraints. And happy to chat about that as well offline maybe. Yeah.
Lauren, let me take two questions from the Q&A. One, they're both excellent questions. One you will have thought a ton about, and one maybe not so much about. The first one is by Renee Diaz de Leon. In the context of the crop fluctuation problem, how local are the markets for these crops? To consider general equilibrium, should we think at the municipal level, the national level, or the regional level? That's the first question. That's the one I think you thought about a bunch about. The second one is from Emmanuel Murray Leclerc. I was wondering if the speaker had some insights on the use of observational plant data, which are abundant in manufacturing. Pete Klenow had a long list of such publicly available data sets to learn about technology diffusion empirically. So I guess that's a little bit of a swing because it's thinking about plant data and observational data. Go ahead.
Yeah. So on the first point, yeah, about how integrated are these markets? So, we haven't done this exercise, but this is what I was saying. I really think this would be sort of a neat exercise that you could do with studies like this. So we find, local price effects from local storage that suggests that these markets are pretty poorly integrated, meaning that sort of the right context to think of a market is a very local level. There's been other work, actually. Ted has another paper in a slightly different part of Kenya, where he's looking at price effects for different goods, looking at doing a randomized saturation design with give directly of giving cash transfers. And there they don't find big price effects of local sort of infusion of cash or which can generate in some cases supply shocks. So there's some conflicting evidence there. And I think thinking about developing a model to actually infer from the price shocks that are seen, what does this mean for different goods, for example, in different locations? What does this mean about how integrated markets are? I think there's lessons that could be taken if you could apply a model to thinking about that. For now, when you're actually in practice doing randomized saturation designs, this is a huge issue. And frankly, a lot of it's a little bit, ad hoc based on your particular knowledge of the particular context, at what level you want to randomize. I will say this last paper I've mentioned here, which is looking sort of at how do things change at scale. This is trying to basically model kind of price effects and how they're getting transmitted across locations and taking price data and trying to back up trade costs and the like. Our hope is that eventually, and this is still a bit of a work in progress, but almost ready. And our hope is that this could be a model you could use to almost do like power calculations for, when you make certain assumptions about how integrated markets are, what trade costs look like, et cetera, then what's the right level at which to do your randomized saturation design. So again, power calculations are always sort of guess ahead of time. You make a guess about what you're going to see, but it could maybe help inform that decision on a practical note. And I think then conversely, taking models to kind of apply it to existing results would be very interesting. So that was the first point. The second question was about sort of observational data. So I have mainly shown you RCTs here just because there's been such a huge abundance of them. But of course, there's also a ton of observational data looking at, misallocation. For example, Doug and Chris Udry have a paper on misallocation, looking at input use at a actually plot by plot level. So one nice feature of this is you have many of these data is you'll have not just for individual households we have data, but you'll have data for different plots the same household is growing, and that's actually quite an interesting data set to look at. Chris Udry also has work looking at diffusion of agricultural technologies based on your network using observational data. So there is a lot you can do with observational data. It's particularly nice if you have variation that's exogenous coming from RCT. Plant data, there's a lot. I didn't go over technology adoption, I should say, in manufacturing, but there's a lot of work there. So for example, David Atkin has a work on with several other co-authors on soccer balls in Pakistan and adoption of a new cutting technology for those soccer balls. That's also an RCT. I'm trying to think about observational data, but I think there's a lot you can do if you think about kind of knowing the network and how these firms are connected. But then you have to find some sort of plausibly exogenous shock, which can come from natural experiments as well as RCTs.
Okay, thank you very
Hello.
much.
Have some question?
Unfortunately. Somebody, I'm sorry. Did I cut somebody?
Yeah, I have some question.
Oh, okay, go ahead. We'll take one last one.
Okay, thank you. My name is Emmanuel. Most of the studies tend to focus on a single intervention that address adoption constraints. For example, giving subsidies to farmers. And yet we know that actually farmers face so many production risks. They also face so many market risks. An example is input quality that is always a problem in developing countries, but also output prices tend to fluctuate. Then farmers also face weather uncertainty, for example. Now, many researchers tend to focus on a single intervention, yet farmers face a multiplicity of so many challenges. Doesn't this require a bundling of interventions that address different problems so that adoption constraints can actually be resolved? And then if we focus on one intervention, are we surprised then to see low adoption of technologies in developing countries if we tend to offer only one intervention to address so many challenges?
Yeah, it's a great
Thank
question.
you.
So there could be interplays between these constraints, and it might be that you have to address all these constraints simultaneously, or at least some in combination to get the effect. And in some ways, I think there's been a bunch of reasons that we haven't had as much of that, having to do with both the fact that it's difficult, you're limited for power, and so you have to choose certain arms. There's also, I think, some unfortunate kind of academic incentives in terms of publishing about really wanting to nail down what is the barrier that stops people from doing kind of overall bundled interventions. There's been some attempts to try to look at interaction terms, right? So for example, the Karlan et al. Piece that we looked at does try to look at risk, the interaction of risk and credit constraints. So what happens when you alleviate both? And it looked like for fertilizer, that does seem to have a bigger effect. And for others, you didn't see a significant interaction term. So there's been some attempts, but sort of if you want to kind of parse out both the different barriers as well as the interaction, that's just going to add, it's going to be more difficult in terms of power. I will note one piece, if you're interested in kind of thinking about alleviating multiple constraints at once, there's a nice piece by Maya Duru and her co-authors looking at actually the same NGO that we looked at in our storage paper. And they offer a variety of services that try to address actually all three of those constraints. So credit, risk, and information all at once. And they find very big effects from doing all three at once. So there have been, I think, that's a very new paper, and there have been new attempts to move in that direction. But I agree, it's an understudied area of how do these constraints interact.
It was a good last question. I'm glad we took it. Unfortunately, we're out of time. I want to thank Lauren and Eleanor, and tomorrow we do not have, let's unmute and clap. Yeah, there we go. Tomorrow we don't have class respecting the Easter weekend for the UK, but we will return next week, Wednesday. Eleanor will have her session, and then Thursday and Friday we'll have more sessions. So also another thank you to Mandy and Kirsty and Lauren. We'll see you all next week. Bye-bye.
Thanks, everyone.
Thanks, Lauren. Great presentation. Just wonderful.
Is she there still?
Maybe not. Maybe not. And thanks, Eleanor.
Thank you.